Hello and welcome to this lecture series. Today we are going to start with the lectures on sequence and series. And in this first lecture on sequences, we are going to talk about infinite real sequences. That is, the sequences which are infinite in one direction and finite in the other. Okay. That means the sequence has the first element but no final element. Okay. Why I'm saying this is because also there are sequences which are infinite in both directions, and we call them bi infinite sequence or doubly infinite sequence. And also we can have finite sequences. Okay, so but we are going to deal with today are one-sided infinite sequences. Okay, so to start with the sequence of numbers. So a sequence is a collection of objects. Okay, so it's a like a list of numbers a1, a2, a3, so on, an, and so on. Okay, so in this sequence the repetitions are allowed. Okay, and the elements may be same. Okay, but the order really matters. Okay, so it has a particular order. uh, these a1, a2, a3, they are called the elements of the sequence. Okay, and the same element can appear multiple times at different position in the sequence. uh, the position of the element in a sequence is its rank, or called as its index, which is a natural number for which the element is the image. Okay, so like uh, 1 is the index of the first element. Okay, this is the second position, third position, so correspondingly a1, a2, a3 are the images uh, or the elements. Okay, so these elements of the sequence we often denote by this an or bn or cn, where the subscript n denotes the position of the element in the sequence. Okay, so like if I write this as an here, that means the position is the nth position in this sequence for this element. Okay, so there are different representations by which we can write sequences. Two of them are written here. One is by listing the elements of the sequence, or simply by specifying the nth term, where n can vary from the positive integers 1, 2, 3, and so on. Okay, so like first sequence is given as an example here as 1, root 2, root 3, root 4, so on, root n, so on. Okay, so it's a sequence. And or we can simply write this by specifying that the sequence is an with nth term an given by root n, and if you take n value 1, 2, 3, so we get all the elements of the sequence. Okay, so similarly we can have another sequence, say 1 half, 1 by 3, so on, 1 by n, so on. Or we can simply represent it as an is equal to 1 by n with n varying as 1, 2, 3, so on. Okay, so we get this sequence. So there are a number of examples. We can have positive terms, or we can have alternate positive negative term sequence, like 1 minus half, 1 by 3 minus 1 by 4, so on is the nth term. So we can simply write the nth term, and we can say that it's a sequence when n is 1, 2, 3, and so on. Okay, or again another sequence. Okay, and as I said, the elements can be repeated elements, so they can occur multiple times. So this sequence 3, 3, 3, 3, so on, 3, so on. This is also a sequence. Okay, and we can simply specify an as 3, where n varies as 1, 2, 3, so on. So we represent this sequence. and say maybe 2 4 8 so on to power n. Okay, so it's again a sequence with the n term simply written as n as 2 power n. So what we are seeing here is that these numbers n equal to 1 2 3 so on, they act as a uh, domain, and so we can represent it like a function. Okay, so they act as a domain, and the elements these are in the range, okay, of the function. So we can define infinite sequence of numbers as a function whose domain is the set of integers greater than or equal to some integer n. Okay, so specifically here we said with n is equal to 1 2 3, but it may be for starting with n is equal to say 6 and 6 7 8 so on. So domain is the set of integers greater than or equal to some integer capital N, and so sequence is a function whose domain is this, and then we have these elements as the sequence elements. So this is by listing or specifying the nth term. uh, we can also represent the sequence graphically, and say for example if you have this sequence 1 half 1 by 3 1 by 4 so on 1 by n and so on. So there are two very common ways to represent them graphically. Is one is that you simply uh, represent these elements on the real line. Okay, so if you take a real line and then we just write the first element as a1. Okay, so first element is 1. Okay, so 1 here, right, so that's a1. Second element is half, so half is here a2. Okay, so third element is 1 by 3, so you have 1 by 3 a3 here. Then fourth 1 by 4, then fifth will be 1 by 5, and then you will have 1 by 6 1 by 7 and so on, 1 by n and so on. Okay, so we can represent the sequence on the real line, or there is another way that we can represent it on the xy plane, where x-axis is taken as the domain which is positive integers, and the y-axis is taken as the an elements. Okay, so we can like represent these members, because this is corresponding to n1, this is for n2 n3, first position second third and so on. So we can represent the members as 1 comma 1 or 1 comma a1, then 2 comma a2, 3 comma a3, 4 comma a4, 5 comma a5 and so on. Okay, so when n5 this is a5. Okay, simply when n4 this is a4. Okay, so we can represent so on a6 a7 and so on. Okay, so basically there are two ways we can represent it on the real line, or we can represent it on the xy plane. Okay, say for example we take another here, say 1 root 2 root 3 root 4 root n. So the first element a1 is 1, then the second element is root 2, third element is root 3, then we have root 4 which is 2, then root 5, root 6, root 7 so on. Okay, or we can represent it on the xy plane. So it's a root 1 which is 1, then root 2 root 3 root 4. Okay, so when fourth position is root 4 which is 2, root 5 root 6 and so on. Okay, third example is we have a alternate positive negative sign. So if you can again represent this on the real line as first element is 1, second element is negative. Okay, so on the negative side a2 which is minus half, and third element is 1 by 3, fourth element minus 1 by 4, fifth as 1 by 5, then we'll have sixth here minus 1 by 6, 7 on this side 1 by 7, then minus 1 by 8 and so on. Okay, it will get closer and closer to 0. And similarly on the xy plane, so when n is 1 we have a first number 1, when n is 2 we have second number minus half, so it goes below the axis. When n is 3 it becomes 1 by 3, we then 4 minus 1 by 4 plus 1 by 5, then minus 1 by 6 plus 1 by 7 minus 1 by 8 and so on. Okay, so you can see that here like numbers are decreasing going towards 0, the numbers are increasing going towards plus infinity. Here the number are alternately changing sign, but they are like going towards a uh, fixed point as n becomes large. Okay, so that's where the concept of convergence or divergence of sequence comes. Okay, and by convergence of a sequence we mean that as n becomes large or n increases, the numbers in the sequence they approach a single finite value. Okay, so if the sequence do not approach a single value, or if it do not approach a finite value, then we say that it is a divergent sequence. Okay, so like the convergence and divergence of a sequence, whether the sequence converges. Converges means that it goes to a single finite value when n becomes large. Okay, as with n increasing. Okay, and divergence means that either it is not going to a single finite value. Okay, or it is not going to a finite value at all. Okay, so for example, let us see this first graphically, then we'll talk about this mathematically. Say you are given this sequence 0, second element half, then 2 by 3, 3 by 4, in general nth element n minus 1 by n, and so on. Okay, so if you represent this on the xy plane, then first element is here when n1 uh, element is 0, so 1 comma 0, then 2 comma half, 3 comma 2 by 3, fourth element 3 by 4, fifth 4 by 5, and so on. Okay, so these when n becomes large, it will go closer and closer to 1. Okay, but it will never cross 1. Okay, it will never go above 1. Okay, so this sequence converges to 1 because when n becomes large and large, this value goes, these elements goes close and close to 1. Okay, so they are like converging to a finite value and a single finite value. Okay, so you take another example, say this uh, 0 minus half, 2 by 3 minus 3 by 4, so on this. Okay, so as n increases, the positive terms they are trying to approach plus 1, the negative terms are trying to approach minus 1. Okay, so if you see uh, this is the first element 1 0. Okay, when n is 2, the value is minus half, so this value with n3 it goes to 3 comma 2 by 3, then 4 comma minus 3 by 4, 5 comma 4 by 5, 6 comma minus 5 by 6, then 7th will be plus 6 by 7, then 8th will be minus 7 by 8. So you see the positive terms, they are next positive will be here, and they are going towards plus 1. Okay, and these negative terms are going towards minus 1. So when n goes to becomes too large, then the positive values will be very close to plus 1 and the negative values will be very close to minus 1. So because they are not approaching a single finite value. Okay, so we say that this sequence is a divergent sequence. Okay, so this sequence is diverging. Similarly, I have this sequence 3 3 3 3 so on 3. Okay, so with the n large, this is a constant sequence. Okay, so it will continue to converge to 3, it will always take this value. Okay, so it's a converging sequence. Okay, so what's important here is that the convergence or divergence of a sequence has nothing to do with how the sequence begins. Okay, whatever way it begins, the important part is how it behaves when n becomes large. Okay, so it depends only on how the tail of the sequence behaves. Okay, what happens when n goes to uh, keeps on increasing, n becomes too large. Okay, so that means that the convergence or divergence of a sequence is not affected by the values of any number of initial terms. Okay, so if you are given a sequence, so even uh, if you do not consider some of the initial terms, still the sequence will converge or diverge depending upon what happens when n goes to too large. Okay, so like when n goes to, in the concept of limit, when limit n goes to plus infinity, what happens to the uh, value of this sequence? If this gives a finite single value, okay, single finite value, then we say it is convergent, and if it does not do so, then we say it is divergent. Okay, so now mathematically, this a sequence an converges to the number L if to the every positive number epsilon there corresponds an integer n such that for all n greater than n implies that the uh, an minus L modulus is less than epsilon. Okay, that means the distance of uh, the elements of sequence from L uh, is less than epsilon, or the elements of the sequence lie within the epsilon distance from the L. Okay, so they lie in the band within the epsilon distance from the L. Okay, and if no such L exists, okay, we say that the sequence diverges. Okay, if sequence converges to L, we write limit n tends to infinity an equal to L, or simply we write an uh, goes to L. Okay, and we call L the limit of the sequence. Okay, so what we mean here is that if we plot the points on the real line, so say this is the first element, second element, third element, then you have fourth, fifth, so on. Okay, so it doesn't matter how it starts, but there exists a integer capital N such that when n is greater than capital N, so after this point, okay, for integer capital N the corresponding element is n. Okay, so after this element, all the elements lie within the epsilon distance from the L. Okay, so if is the L is the number, then within the epsilon distance means L minus epsilon to L plus epsilon. All the elements after this element lie within this range. Okay, so then we say that this limit exists or the sequence is convergent. Okay, or we can also talk about this in 2D plane, that it doesn't matter how it starts. Okay, so there's your a1, a2, a3, a4, so on, but there exists a integer n. Okay, so there is a point n at which the element is an. After this element, all the elements lie in the band which is epsilon within the L. Okay, so if this is your L, then L minus epsilon is this and L plus epsilon is this. So all the elements after this position, all the elements, okay, with n becoming large, all the elements lie within this band. If this is true, then we say that limit n tends to infinity on the sequence an equals L. Okay, or L is the uh, limit of the sequence, and we say that the sequence an converges to this L. Okay, so this is the definition, and so this also means that if an converges to L, then that means this is possible when y is equal to L is the horizontal asymptote of the sequence of points n comma an. Okay, so this acts as a horizontal asymptote for this sequence when n goes large. Okay, and in figure all the points an's after a of n, okay, all the points these after this point n lie within the epsilon of L, okay, lie within the epsilon distance of L. That is true from this definition, that modulus of an minus L is less than epsilon. So we know how to solve this modulus. Okay, that means minus epsilon less than this less than epsilon, and then we can take L to both sides. So an values are lying between L minus epsilon to L plus epsilon. That's what is shown here. Okay, so let us take one example now, that using the definition of convergence show that limit n tends to infinity 1 by n is 0, where this 1 by n is the nth term of the sequence. Okay, so to prove by definition, definition says that let epsilon positive be given, or for every positive epsilon we want to show that there exists an integer capital N such that for all n greater than this, okay, the sequence in minus the limit value is modulus is less than epsilon. Okay, that means uh, after this point all the terms of the sequence lie within the epsilon distance from origin, okay, or the 0. Okay, so we have done this thing in functions also, in one dimensional functions. Okay, and we know how to solve this. Okay, so a similar concept for sequences we are going to use. We'll solve this epsilon inequality and we try to find what the value of integer we can take. Okay, so if you solve this modulus of 1 by n less than epsilon, uh, then 1 by n less than epsilon can be written as n greater than 1 by epsilon. Okay, so if we choose the n to be an integer which is greater than 1 by epsilon, then both these conditions will be automatically satisfied. Okay, so if n is any integer greater than 1 by epsilon, the implication will hold for all n greater than n. Okay, so for all n greater than n and n greater than 1 by epsilon, these two will be automatically satisfied. Okay, and this proves that limit n tends to infinity 1 by n equals 0. Okay. uh, Now there are certain results which hold true. Okay, and we have seen these results previously also in functions. Okay, so the concept follows here also, that let there is a sequence an and there is a sequence bn of real numbers, and let a and b be real numbers. The following rules hold if the sequence of an is convergent and this limit n tends to infinity bn is b. Okay, then the first is the sum rule, that the limit n tends to infinity an plus bn is a plus b. Okay, that means if sequence an and sequence bn are convergent, then the sequence an plus bn is also convergent and it converges to a plus b. The difference rule, that limit n tends to infinity an minus bn is a minus b. The constant multiple rule, that the limit n tends to infinity k times bn is k times b, k any number. Okay, product rule, that limit n tends to infinity n times bn is a times b. And the quotient rule, so limit n tends to infinity n by bn is a by b if the denominator is non-zero. So all these rules hold true. Okay, so we can utilize them if we know that there are two sequences which are convergent, then there's some difference, a constant time sequence or the product of sequences or division of sequences, we can calculate their uh, convergence. Okay, the another important result we did earlier is the sandwich theorem. So we also have sandwich theorem for sequences, and it says that let uh, an, bn, and cn be sequences of real numbers, and if the an is less than equal to bn is less than equal to cn, this holds for all n beyond some index n. Okay, so after some point this condition holds for all n after this point. Okay, and if you know that the sequence an, the first sequence and the third sequence, if your sequence an is convergent and sequence cn is also convergent and they converge to the same point, then the sequence bn also converges to the same point. Okay, so the scenario looks like this. Okay, so it doesn't matter what happens initially, but after some point, if this is true that the ans are less than bns and bns are less than cns, and if these ans and cns are converging to is L, then this Bn's will also converge to L. Okay, so we'll just prove this mathematically, since sequence Cn is convergent to L and sequence Cn is convergent to L. So by definition of convergence, for every epsilon positive, there exist positive integers n1 for one sequence and n2 for the other sequence, such that for all n greater than n1, uh, the ans lie within the epsilon distance from L, okay, and for all n greater than n2, the cns lie within the epsilon distance from L, okay. So if we choose uh, capital N to be the maximum of these two integers, okay, then for all n greater than capital N, okay, so if you have n1 here and n2 here, so we choose n2 uh, to be capital N. So after that point, uh, both these will be true, and because this condition is also given, so we can combine these three conditions. So from the first condition, uh, L minus epsilon will be less than an, and an is less than bn, and bn is less than cn, and from this third condition, cn is less than L plus epsilon, okay. So we can write this that L minus epsilon is less than an, this from this condition here, and an is less than bn is less than cn, this is given, and cn is less than L plus epsilon from this second condition, okay. And so what we have is that L minus epsilon is less than bn is less than L plus epsilon, okay, or we can write this as bn minus L modulus is less than epsilon. That means for all n greater than capital N, bn's lie within the epsilon distance from L, which is the definition of convergence of sequence. So it immediately implies that the sequence bn converges to L, and so we can write limit n tends to infinity bn is L, okay. So this was one important result, okay. The There's one more important result. There is a theorem which says that suppose that fx is a function defined for all x greater than equal to n naught, and that sequence an is a sequence of real numbers such that an equals f of n for n greater than equal to n naught, okay. So the points on this sequence lie on the curve fx for all n greater than equal to n naught, okay. Then uh, the limit x tends to infinity fx equal to L implies that the limit n tends to infinity an equals to L, okay. So if the function converges to L, then the sequence also converges to L, okay. So this is obviously true because the points are nothing but the points on the curve, but only at the integer positions, okay. The function is defined for all x, okay, but the sequence is defined for integer values, okay. So now we can prove this, okay. Suppose that the function converges to L, okay. So by definition of convergence of function, okay, the for each positive number epsilon there is a number m such that for all x greater than m implies the uh, function lies within the epsilon distance from L, okay. So that's the definition of convergence of a function for x going to plus infinity, and uh, if we choose n to be an integer greater than this m, and greater than or equal to n naught, because this is defined only for n greater than n naught, okay. Then for all n greater than n, uh, an equals to fn, this will hold because n is greater than n naught, and it holds for all n greater than n naught. And because this holds, so this modulus an minus L can be written as modulus fn minus L, because an equals fn, and this modulus is less than epsilon because the function values fn and fx are same for n greater than n, okay, n greater than n naught, or same for n greater than n. So this is less than epsilon, and so this proves the definition of convergence of sequence, that n greater than n implies modulus of n minus L less than epsilon, okay. So that means limit n tends to infinity n is L, okay. Now this theorem formalizes the connection between the limit of sequences and limit of functions. So now we can utilize the L'Hopital rule to find the limit of some of the sequences, for which we can write the corresponding function such that the points on the sequence lies on the curve. Okay, then we can actually use L'Hopital rule to find the limits. Say for example, show that the limit n tends to infinity log n by n equals 0. Okay. So the function log x by x is defined for all x greater than equal to 1, and this agrees with the given sequence at positive integers. Okay, so for n1, n2, n3, the values of the sequence will lie on the curve of log x by x, and if we calculate the limit of this function, then that will also be the limit of this sequence. Okay, so and for this function we can apply L'Hopital rule, because when x goes to infinity, this is the infinity by infinity form. So L'Hopital rule says that we can take one derivative of numerator and one derivative of denominator, and then apply the limit. Okay, so this limit is same as derivative of log x, which is 1 by x, and derivative of x, which is 1, and when x goes to infinity, this 1 by x is 0. Okay, so limit of this function is 0. Okay, and so by just previous theorem, the limit of the sequence is also 0. Okay, so that gives our result. Okay, so now I'm giving you some important results which you can remember, and you can try and find prove them too. I'm not giving the proofs. One is already given, this limit n tends to infinity log n by n is 0. Okay, the second is limit n tends to infinity x power 1 by n is 1 for x positive. The limit n tends to infinity 1 plus x over n whole power n is e power x for any x. Okay. The fourth is limit n tends to infinity nth root of n is 1. Uh, Fifth is limit n tends to infinity x power n is 0 for all x such that modulus of x is less than 1. That means x lying between -1 and 1 with strict inequality. And limit n tends to infinity x power n over n factorial is 0 for any x. Okay, so these are 6 important results which will be used a lot in sequences, as well as later we'll study series, so they will be utilized there as well. Okay. So like in the beginning we said, there are two ways we presented for representing a sequence. Similarly, there are many more, and one of them is the recursive definition of sequences. That means sequences are often defined recursively by giving two things. One is that the value of the initial terms, okay, uh, the first few terms you can say, and a rule called recursive formula for calculating any later term from the terms that precede it. Okay, so calculating the further terms by using a formula based on the previous known terms. Okay, so for example, the statement a1, the first element is 1, and the nth element is uh, n minus first element plus 1 for n greater than equal to 2, is this is a recursive formula, because it is based on given one initial element, and all further elements depends on the previous known elements. So for n equal to 2, this will be like a2 equals a1 plus 1, and because a1 is known, we will get a2. Then for n is equal to 3, we get a3 is a2 plus 1, and because a2 is calculated, so we can calculate a3, and so on. Okay, so if you start plugging n2, n3, n4, n5, so on, we'll get the actual sequence, which is 1, 2, 3, so on and so on of positive integers. Okay, so similarly, the say for example a1 is 1 and an is n times an minus 1 for n greater than equal to 2. So again it's a recursive definition, and with n is equal to 2, we get is a2 is 2 times a1, so a1 is known, so we get a2 as 2. Then n is equal to 3, so we get a3 is 3 times a2, a2 calculated 2, so 3 times 2 is 6, so we get the third element, and so on. Okay, so what we get is 1 2 6 24, so on, and factorial. Okay, so it's a factorials of positive integers. And say one last, the very famous Fibonacci numbers. Okay, so given a11 and a21, a of n plus 1 is an plus an minus 1 for n greater than equal to 3. Okay, so it depends on the preceding two numbers. Okay, sum of preceding two numbers. So what we will get is the third element as sum of these two, so 1 plus 1 is 2. Then fourth element is sum of these two, so get 3. And fifth element is sum of previous two, so 5. The next element will be 8. Then we will have 13, and so on. Okay, so these are all recursive definitions of sequences. Okay, and these formulas are frequently arise in computer programs and numerical routines, where you use them for computation of, say for example, differential equations. Okay, or something like that. Okay, the next definition is the subsequences. Okay, so a subsequence is a sequence that can be derived from another sequence by deleting some or no element without changing the order of the remaining elements. Okay, for example, consider the sequence of positive integers 1 2 3 4, so on and so on. Okay, so the subsequence of even integers, okay, we can obtain this by deleting the odd positions, elements in the odd position. So if we eliminate 1 3 5, so on, and keeping the order of these elements. Okay, so what we'll get is 2 4 6, so on, 2, and so on. Okay, so it's a subsequence of the positive integer. Similarly, the subsequence of odd integers, this is a subsequence of this. Okay, by deleting these 2 4 6 and keeping the order. Okay, similarly, the subsequence of primes. Okay, so the numbers which are non-prime, if we remove them and keep the order, we will get this. Okay, so all these are subsequences. Okay, so if a sequence an converges to L, then all its subsequences converges to L. So that's an important result. Okay, and so we can figure out the limit L of a sequence an by examining the limit of the particular subsequence of an. And also, if you can prove that any subsequence uh, an diverges, then the sequence itself diverges. Okay, so if you have a subsequence which is divergent, then original will be divergent. And also, if you can prove that there are two subsequences of a sequence having different limit, then the sequence is divergent, because uh, for convergence it must converge to a finite unique value. Okay, so if you have this as two subsequences, and if they are converging to different values, then the original sequence is divergent sequence. Okay, and we have already seen this as an example, say sequence of 1 minus 1 1 minus 1 1 minus 1, and so on. So if you take a subsequence of 1 1 1 1 1, it converges to 1. And if you take another subsequence of minus 1 minus 1 minus 1, so on, it converges to minus 1. Okay, so there are two subsequences converging to two different limits. So the original, which is 1 minus 1 1 minus 1 1 minus 1, and so on, it is a divergent sequence. Okay, there are two important concepts, okay, which play a key role in determining the convergence of sequence. And one of the concept is the boundedness, and the other is the monotonic sequences. So first, let us take this definition of bounded sequence. A sequence an is bounded from above. Okay, if there exists a number m such that an is less than equal to m for all n. Okay, so we say that a sequence is bounded from above if all the elements of the sequence are less than a number, okay? And in that case this number becomes the upper bound of the sequence. And because there can be infinite upper bounds, okay, uh, if m is an upper bound of an but no number less than m is an upper bound of an, then m is called the least upper bound for n, okay. Okay, so if you have infinite number of upper bounds of n, then the one below which there is no other upper bound will be called as the least upper bound of the sequence. Similarly, we can define a sequence which is bounded from below if there is exist a number m such that all the elements of the sequence are greater than this number, okay, are greater than equal to this number for all n, and so this number will be called a lower bound of an. And if this there is no other lower bound which is greater than this, okay, so if m is a lower bound of an but no number greater than m is a lower bound for this sequence, then m is called the greatest lower bound of the sequence, okay. So if you have infinite lower bounds, then which one is the uh, greatest lower bound, that will be called the greatest lower bound of the sequence. And we call any sequence as bounded sequence if it is bounded from above as well as below, okay. So whenever we write that sequence is bounded, then it is both bounded above and below, okay, else we only say that it is bounded from above or bounded from below, okay. Now there is a important result that every convergent sequence is bounded, okay. So this one result is important, okay, but the converse is not true, okay. There are bounded sequences which are not convergent, okay. So let us prove first that every convergent sequence is bounded. And for proof, let a sequence an is there and this sequence is convergent and converges to a limit L, okay. So by definition of convergence, for every epsilon positive there exists a positive integer capital N such that for all n greater than equal to capital N, the implies that the elements a n lie within the epsilon distance from L, okay. And so we can also open the right hand side and write that the points an, okay, the elements an lie in the band between L minus epsilon to L plus epsilon, okay. Now for n greater than equal to capital N, the elements are bounded by these two, okay. So we are only left with the elements which are for n less than this n, okay. So if we take g to be the minimum of a1 a2 so on a of n minus 1 and L minus epsilon, okay, so it covers all the elements of this sequence, okay. So because L minus epsilon is uh, the less than all n's n greater than n, and for these elements, so whichever is the minimum we call it g, and similarly capital G as the maximum value of L plus epsilon and a1 a2 so on an minus 1. So for all n we have that g is less than equal to an is less than equal to capital G, okay. So because an for all n greater than this is true, and for all other values we have taken this as minima and this as maxima, so uh, all the values or all the elements of the sequence they lie between g and g, okay. So which proves that the sequence is bounded, okay. But the converse is not true, as I said that we have bounded sequences which are not convergent, and for example say an is equal to minus 1 raised to power n, so this sequence we already said like minus 1 1 minus 1 1 minus 1 1, okay. It's a bounded sequence, okay. uh, all the values are less than equal to 1 and all the values are greater than equal to minus 1, okay. So there is a least upper bound of 1 and there is a uh, greatest lower bound of minus 1, but the sequence is divergent because there are two subsequences giving two different limit values. Okay. Okay. The second important definition is the monotonic sequences. Okay. So when we say monotonic, that means the non-decreasing sequences or the non-increasing sequences. So first definition is the non-decreasing sequence. So a sequence an with the property that okay, here we have to use the symbol. Okay. With the property that the uh, an is less than equal to an plus 1 for all n is called a non-decreasing sequence. Okay, so with n uh, moving from 1 to 3 so on, the corresponding values are greater than equal to the previous values. Okay, so like a sequence of integers, positive integers 1 2 3 4 5 6 so on, it's a non-decreasing sequence. Okay, say for example, take some examples here. Okay, say the sequence of natural numbers 1 2 3 so on and so on, it's a non-decreasing sequence because the next element is always greater than equal to previous element. Okay, this is true for all elements, and this has particularly no upper bound. Okay, but say the sequence is 1 by 2 plus 2 by 3 plus 3 by 4 plus 4 by 5 and so on, n over n plus 1. So the next number is greater than equal to previous number. Okay, and this is always true for every element. Okay, and so it's a non-decreasing sequence, and for this particular there is a upper bound. Okay, uh, which is bounded above by 1. Okay, similarly, the constant sequence 3, 3, 3, 3, 3, it also satisfies this condition. Okay, there is the equality here. Okay, so this number is greater than equal to this number in case equality is here. Okay, so it also satisfies this definition. So it is also a non-decreasing sequence. The other definition is non-increasing sequence. Okay, a sequence an with the property that the next number is always less than equal to the previous number for all n is called a non-increasing sequence. Okay, so for example, the sequence 2 3 by 2 4 by 3 5 by 4 and so on, n plus 1 by n. Okay, so like this number is less than equal to this. Okay, this is less, third is less than second, fourth is less than third, and so on. So it's a non-increasing sequence. Similarly, 1 half, 1 by 4, 1 by 8, so on, 1 by 2 power n, and so on. Okay, so it's a non-increasing sequence. And again, this sequence of constant 3 3 3 3, it also satisfies this condition. Okay, because of the equality, so it is also a non-increasing sequence. So that means the constant sequence is a non-decreasing sequence as well as a non-increasing sequence. Okay, and the sequence an is monotonic. Okay, so we call any sequence as monotonic if it is either non-decreasing or non-increasing. Okay, so either of these is true, then we say that it is monotonic. Okay, and of course there are sequences which are non-monotonic. That means they are neither non-decreasing neither non-increasing. For example, the sequence 1 minus 1 1 minus 1 1 minus 1. Okay, it is not monotonic. Okay, because the second number is less than this but the third is greater than second. Okay, so both properties are not satisfied for all n. Okay, so now this finally a very important theorem, which is the uh, monotonic sequence theorem, and it says that if a sequence an is both bounded and monotonic, then the sequence converges. Okay, so previously we said that every convergent sequence is bounded. Okay, but we said that there are sequences which are bounded but not convergent, so converse was not true. But if we add a condition here that if a sequence is both bounded and monotonic, then it is definitely convergent. Okay, we'll prove this result. Suppose there is a sequence an is non-decreasing. Okay, so there is a monotonic sequence with non-decreasing. And similarly you can prove this for non-increasing with the same concept. Okay, so and let L is the least upper bound. Okay, so it's a non-decreasing sequence, and uh, because it is bounded, okay, so it is bounded from above, so let L is the least upper bound, and we plot the points 1 comma a1, 2 comma a2, so on in the xy plane. Okay, and if M is an upper bound of the sequence, then that means all these elements a1, a2, a and so on will lie below the line y is equal to M. Okay, so maybe there is a plot here. Okay, so let these be a1, a2, a3, so on points. Okay, and if M is an upper bound of this, okay, then all the points will lie on or below M. Okay, and because y is equal to L is the least upper bound, so this is also true for y is equal to L. That means all the points of this sequence, okay, they will lie on or below this line y is equal to L. Okay, okay, so the line y is equal to L is the lowest such line. Okay, the line of least upper bound. So none of the points n comma n lie above y is equal to L. Okay, so all the points must lie below this. Okay, but some do lie above any line lower than this y is equal to L minus epsilon, because now this line is not a upper bound, so some point uh, will lie above that L minus epsilon line. If this is not true, then L minus epsilon will become a upper bound, and y is equal to L will no longer be the least upper bound. Okay, so there must be some points which will lie above this line. Okay, if all the points will lie below this L minus epsilon, then L minus epsilon will become the upper bound, and because it is less than L, so it becomes the least upper bound, but L is the least upper bound, so some points must lie above L minus epsilon. Okay, for any epsilon positive number. Now this sequence converges to L, okay, because of these two, that the points in the sequence n are less than equal to L for all values of n. Okay, because L is the least upper bound, and given any epsilon positive, okay, there exists at least one integer n, there exists at least one point n, after at that point the element value is greater than L minus epsilon. Okay, so there is at least one n at which the corresponding value is above L minus epsilon, because if it is not true, then it becomes the least upper bound. Okay, so there is at least one such point, and because it is given that it is monotonic, non-decreasing, so after this point all the values must lie above this L minus epsilon. Okay, so that way we are going to prove. Okay, the fact that sequence an is non-decreasing further tells us from the second condition that ans must be greater than equal to an. That's how the non-decreasing function definition is, and because an is greater than L minus epsilon, for all n greater than equal to capital N, this holds. Okay, so for all n greater than this, all the ans must be greater than an point, and that is greater than L minus epsilon line. Okay, and so the points an beyond this point n lie within the epsilon of L. Okay, so after this point all the points of the sequence lie within the epsilon distance of L, and that's exactly is the definition of convergence of the sequence. And so we have that the sequence an converges to L. Okay, so similarly you can prove for the non-increasing sequence which is bounded from below. Okay, with the same concept. Okay, and importantly this theorem says that every sequence which is bounded and monotonic is convergent. Okay, but this do not say that every convergent sequence is monotonic. Okay, that is not true. Okay, so theorem does not say that convergent sequences are monotonic. Okay, for example, this sequence converges and is bounded, but it is not monotonic. okay. So you can try plot these points and see why it is not monotonic, okay, because there are some points positive negative and ultimately it converges to 0, okay, but they're bounded, okay, you can check that, okay. So what this theorem does say is that if you have a non-decreasing sequence, it is converges whenever it is bounded from above, okay, otherwise it diverges to infinity, okay. So if you have a non-decreasing sequence, something like this, okay, if it is bounded from above it converges, if it is not bounded from above it will continue and go to plus infinity, okay. Similarly, if you have a uh, non-increasing sequence, something going downward, if it is bounded from below then it will converge to that uh, least greatest lower bound, and if it is not bounded below then it will continue to go down and goes to minus infinity maybe, okay. So this is the concept of convergence of sequences, okay. So I close this now with giving you some numericals to test your understanding. Determine if the sequence is and given by this uh, convergent or not, and also check whether the sequences are monotonic or not, and check whether they are bounded or not, okay. So we close it here, okay. In the next lecture we'll talk about infinite series and its convergence. Till then,